any specific questions on the exam that anyone wants to see?
Yeah. I want to know how you got the negative. I got the right values, but the wrong sign.
On what?
The last question.
Okay.
For the vector. Sorry, partly.
Yeah. Is there anyone else? Shane, have you taken it? You haven't? You guys can stay and I'll just think of it as review and I'll just give you a different version. Yeah. All right, so number 4, any other ones people want to see? On number 4? Okay, yeah, I'll go through number 4 for sure. Any before that? Okay, so exam 2, number 4.
Wait, for the for question 3, the force in that place slot, let it be perpendicular, but we don't. Never mind.
Yeah, I'll draw that real quick too. Okay, so so for number 3, the slot is like this. The force applied by that slot is going to be perpendicular. It could go either of those 2 directions. So it could go this way or the exact opposite. I'll call that RA. There's a weight force. The normal force is perpendicular to the ground. So like that, I'll call that N. And then the cable force is this way. So that's number 3. And then number 4, okay, so there's a 500 Newton force applied at the center. The beam has a length of 1 meter and a mass of 20 kilograms. Calculate the reactions, and then what's the force vector? The beam applies to the pin joint. So Freebody diagram. There's a force up here. I'll call that N. I don't know why I did it in red. There's a weight force of 20 times 9.81, so 196.2. Um, 500 Newton force at the center, and then the pin joint down here, there's a full unknown force vector, I'll call that R. And that's all the loads. And I'm going to use this as the about point. So rho, force, moment. So first I'll do the force R. The rho vector is 0. The components are Rx, Ry. No moment. Then This angle is 30 degrees from the horizontal, the angle of the beam. And so to get from the about point to the midpoint, I guess I'll do the weight first. By the way, anytime two forces are acting at the same point, you could just add up those two force vectors. So you could call this a force vector with a x component of -500 and a y component of -196 and do it all like a single thing. But so the row vector here is -0.433, positive 0.25. The weight force is 0, -196.2. Cross product, so 0.433 times 190. Oh, I see. And you get, I guess the way I did it is, so I did lump these two together. So at the midpoint, this is -500, -196.2. Take that cross product and you get 209.96 positive. Of course, you could separate those into two different forces. You get the same thing when you add them. And then the last one is that normal force. The row vector is -0.866, positive 0.5. The force vector is 0.866 n, 0.5 n, and you get that from, so what you're given is that this angle is 60 degrees. And so if you draw the coordinate system here, the angle that you're given is from the negative x-axis to the incline. So you're given that this angle is 60 degrees. And so a row vector to this vector would be 120. And then the normal is perpendicular to that one. These two are at a right angle from each other. And so you can think of this one as 120 minus 90, and it just gets you back to 30, positive 30. And so cosine and sine of 30 are 0.866, 0.5. Multiply that by n. Take the cross product, and you get negative 0.866 n. Newton's second law says Rx, Ry plus 0.866 n 0.5 n. And then plus -500, -196.2 is equal to zeros. And then the moment equation says 209.96 minus 0.866 n is equal to 0. If you solve these, you get that R is equal to positive 290.04, 74.98. And the normal force N The magnitude is 242.45 newtons. That was for part A. And then part B says, what's the force the beam applies to the pin joint? Well, we know that the force on the beam by the pin is positive 290.04, positive 74.98. And so that means that the force on the pin by the beam has to be equal and opposite of that. So negative 290.04, negative 74.98. Any questions about that one? Okay. Any other problems from the test anyone wants to see? All right. Well, as far as scores go, you know, there's no reason to worry about. I mean, points are not going to be an issue yet for anybody. One of these two tests can still be replaced. So I wouldn't think about it yet so much in terms of points as I would in terms of making sure that you understand stuff. If you are not where you want to be at this point with your scores, there's plenty of time to make that up points-wise, but it's getting late enough that you for sure want to figure out what's not going right, up until now to get the points the way they are, fix those things, and then everything, I think you'll find will just sort of solve itself. But it's really a matter of not getting behind more than it's a matter of points right now. Okay, so that's all for the test. And so now we're going back to joints in 3D. Yes? Oh, yeah. You asked me that before. I'm sorry. So quiz 2. So the first one was, what's the direction of a pulling force or a direction of a cable force? For this one, a drawing would do fine. But the words are parallel to the cable, away from the chosen body. The second one is, what's the direction of a frictionless contact? That's perpendicular to the surface. Toward the chosen body.
So perpendicular just didn't cut it. You needed something a little more.
I needed more because, and here's why. So if you have, let me do it as, so if you have a roller, okay, so say that's a frictionless contact. Perpendicular to that surface is one of those two directions, okay? Right? It could be up toward the body or it could be away from it. And so yeah, that just doesn't specify it all the way. So you need to also know that it's that. And then the last one was for friction contact with friction. That's a force with an unknown direction. Or you could say an unknown force vector, or you could just draw a picture with an unknown force vector. But that's the way those three work. Any other questions? Okay. So back to 3D joints. The last one we did was joint category 4. And what that means is that 4 variables are introduced into Newton's laws. And this is up to 4. This is sort of a weird one. Actually, 5 works kind of like this too, exactly like this. So up to 4 variables introduced into Newton's laws. And the way that works, so that was a pin joint without thrust. And this is an example of that. If you think of this as a single pin joint. So this doesn't allow rotation this way. It doesn't allow twisting this way. It does allow this. That's sort of what it's designed for. And also, well, if you think of translations, it doesn't allow me to translate this forward and backward. It doesn't allow me to translate it up and down, but it does allow translation this way. So that's what it means by no thrust. Thrust is along the axis of the pin. And so this doesn't provide any force along the axis of the pin, okay? And so now we're going on to, oh, and I was gonna say, so now what about the things that, I said that this joint by itself doesn't allow a rotation like that or a rotation like this, okay? But you wouldn't really wanna rely on this joint to provide big couples over and over again to keep this from doing those rotations. You know, it's the same idea as like if you buy a nice door. I don't know if anyone who has kids knows the pain of this one. You buy a nice door, you get it installed, and then you see your kids like hanging all their stuff on the doorknob or like hanging off the top or whatever. It drives you crazy because like the hinges on the door, yeah, they will apply couples that'll prevent the door from rotating down up to a point, but if you keep pushing it, it's going to break, you know? And so this kind of joint is not very good at applying the couples that prevent those rotations. It'll do it up to a point, but if you have 2 joints like this that share the same axis, then instead of applying those couples to prevent those rotations, the pairs of forces will prevent those rotations. So now think of this not as a single pin joint, but think of it as 2 pin joints that share this axis, okay? So if I try to rotate this little stick like this, this pin joint will provide a downward force. This one will provide an upward force. And that's a lot more effective at keeping this rotation from happening than the couple being applied inside the joint itself, okay? And so if you have two of these joints acting with the same axis, then you don't have to assume that the joint's going to apply that couple itself. The forces will take care of that, okay? So that's why if you have two of these joints acting along the same axis, then they don't apply those couples. If you only have one of these, it will apply those couples, but as you're designing it, you better be sure that it's not being relied on to provide too big of couples, or you're going to just rip it right off the wall, you know. So now let's go to joint category 5 that works the same. So joint category 5 is just like the pin joint without thrust. But now thrust is applied, is generated. So this joint applies up to applies, that's not the right word. What did I say before? Joint, sorry. So up to 5 variables are added to Newton's laws. And this joint looks like, so this is a pin joint with thrust. The most likely way that you would see this is like a pin joint with brackets on both sides. Okay. You follow the idea of that? Oh, dang it. Okay, I'm going to leave it alone. And so if this coordinate system, so like say you have the z-axis going along the pin, and the y-axis up, and the x-axis this way. And let's say this is body 1. Then a free body diagram of body 1 looks like this. Well, so let's think about how this looks, and then I'll draw the loads in here. So here's the pin joint I have that applies thrust, and you can maybe see over on your left side, there's little flanges here that prevent this from sliding. Okay. So that's how that thrust is applied. On this one, I could slide it back and forth. There's no force that keeps it from sliding. But here, that can't happen. Okay. And so let's think first about translations. So can I translate this joint that way and that way? No. So there's a force in that direction. How about up and down? No. And now we also can't translate along that pin. Okay. So there's a full unknown force vector applied. There's no translation that's allowed. Okay, so the first thing I'm going to do is draw in those forces, draw in that force vector. So it's like this, and I'll call that, the force F. That's the force on body 1 by body 2. And now let's think about rotations. Can I rotate it like this? No. Can I rotate it like twist it? No. But I can still do this. That's what it's for. And so there's no couple applied about the z-axis, but there is about x and y. And again, with these, I'm going to put them in parentheses. I'll draw it here. So we have a couple in that direction, a couple in that direction, because those are the rotations that aren't allowed. But I'm going to put them in parentheses because those are the ones that aren't always there. So my, and here's mx. Okay. They are only there if there's not a second pin joint along the same axis. Okay. And again, like in the first case, all right, they'll apply those couples, but you don't want your kids hanging on it, Yes?
Can you draw that just with two double arrows on a single arrow, or do you have to draw like you?
Say it again. Can you draw?
Like, can you just, instead of having forced arrows, can you just draw a double arrow line off?
No, because those are only couples. The double arrows mean a couple. So you have to also show that there's a force. Okay, so if there are two pin joints, sharing that axis, then don't include the couples. Okay, so pin joints with thrust and without thrust work the same way. It's just that one has a force along the z-axis. And I keep, all of these, what I'm saying, couples around the x-axis and y-axis and z-axis, that all just depends on this arbitrary coordinate system that I have here. So you're going to have to do problems where it's not the z-axis that pin can rotate around. You're just going to have to, visualize it in each individual problem. How does this thing rotate? This might be the x-axis in some problems, or the y-axis in some problems. So you just have to be able to visualize how are the degrees of freedom restricted by the joint. Find the places where it can't translate or it can't rotate. That's where the loads are applied. Okay. And then the last one is easy. So that's joint category 5. So now that was joint category 5. So now we're on 6. So joint category 6. This introduces 6 variables into Newton's laws. And the only joint like this is a fixed joint. Sometimes it's called a weld joint. And so if you have, something that's just rigidly connected to another body, so this is, let's call this body 1, and it doesn't matter what your coordinate system is, but let's say we have the y-axis that way, the x-axis this way, and that means the z-axis is this way. Then a free body diagram of body 1. There's a full unknown force vector because no translations are allowed. So this is the force on 1 by 2. And then there's a full couple vector because no rotations are allowed. So now there's also a couple component in each of these 2 directions. And you can call that the couple vector on 1 by 2. And actually, now I realize I didn't use that subscript up above. So let's go back here and write well, I don't know. You can write this in the margins or whatever, but this could be represented as m on 1 by 2 y component and m on 1 by 2 x component. You can use that double subscript notation. The reason you use that double subscript notation is because Newton's third law means if you switch those subscripts, you multiply by -1, and it works with couples too, which makes sense because a couple is just 2 forces. So if you switch the subscripts, you're just changing the directions of both of those 2 forces. It changes the direction of the moment. Okay, any questions about any of the joints? All right, let's do a 3D problem. Bless you. Yeah. Okay, so let's say this is like a, how big is this? Yeah, it's sort of like a sign, like on the roof of a restaurant or something. So it's this rectangular shape. And right at the top on the back, it's connected to the wall by a ball and socket joint. That's supposed to be like a little bracket holding the ball and socket joint. Yeah, well, this is what we got. And then there's two cables connected, one here and one here. And the one at the end, maybe that's right, goes to the wall over here. And the one a little closer to the middle goes to the wall up here. Okay, so let's start doing some dimensions. Here's the center of mass, the center of this sign. Okay, that's terrible. Let's see. So what do we know about dimensions? We know that it's 1/2 meter from the end to where that second cable is applied. And it's 2 meters from that line back to the back. And to get from, so both of these cables connect to the wall. So to get from the pin joint to this point here, I'll call that the point B. We have this distance is 2 meters. And this distance is 1.5 meters. Okay, you're gonna have to kind of suspend disbelief for some of these dimensions. And then on the other side, it is 1 meter from here to here. And then that's also 1 meter. Okay, so you're like, hold on. You're telling me that this is only 2/3 as big as this? Okay, you're looking at this for like a funny lens or something. This is the point A. Okay, and the coordinate system we're going to use has the x-axis going, so the origin is at that pin joint. The x-axis goes this way. The y-axis goes up. And that means that the z-axis has to go this way. The mass of this sign is 50 kilograms. And we want to calculate the reactions, the reactions from the pin joint, not pin, it's a ball and socket joint, reactions from the ball and socket joint to the sign, and the tensions in those two cables. Okay, is everyone sort of with me on this? Well, on three-dimensional problems, I think probably the first thing you want to do is just figure out the coordinates of all these points, because it's not really very useful anymore to use cosine and sine to figure out the directions of unit vectors. You know what I mean? So let's just go based on this origin and this coordinate system, figure out the coordinates of the center, and that's where the weight's going to be applied. This point, A and B. Yeah, and that's all we need. And then from there, we'll just be able to subtract vectors from each other, normalize those, that kind of thing. Yeah. The height of the sign. I guess we don't, because the line of action of the weight force is up and down. So, and you can move that force along the line of action. Okay, so let's draw a free body diagram. These can be a little tricky in 3D. So I'm just going to draw it like something with no thickness. Okay, and what are the loads that are applied? There's a weight force that's equal to 50 times 9.81, so 490.5. And then there are two cable forces. One goes this way, I'll call that TA. And then the one at the end goes this way, I'll call that TB. And then the last thing we have is a ball and socket joint. What kind of loads are applied by a ball and socket joint? So think about what degrees of freedom are eliminated by a ball and socket joint. I don't have the thing with me, but that's right, no translation, right? But any kind of rotation is possible. So there's not going to be any couples. There's just going to be three force components, okay? So we have that, and that, and that. And I'll just call this the reaction force R. Okay, how many equations are Newton's laws going to give us? 6 total, yep. And how many variables do we have? 5 in this case. And so this is something that's going to be pretty common in 3 dimensions that we really never see in 2-dimensional stuff. And that is that sometimes, pretty often, not all of the 6 equations are going to be useful, you know? And so I think what we're going to see, I don't really remember this one, but what we're most likely going to see is that one of our 6 equations, when you write it out, just ends up being 0 equals 0. And so we're going to have actually only 5 useful equations to solve for 5 variables. Okay. So let's start writing out this table. Row vector, force vector, and moment. Oh no, I'm sorry. I said first let's come up with all those coordinates. We didn't do that. Okay, so first, the ball and socket joint is the origin. What about A? How do you get to that point A? You see that? So that point A, the coordinates are 0, 1, 1. The point B, x is 0 again. We have to go in positive y direction 1.5, and then in the negative z direction 2. So that's going to be 0, 1.5, 2, negative 2. So B is 0, 1.5, negative 2. Then the center of mass, well, let's label all these points. So we got A, B, let's call this C, D, and then the center of mass, E. What? Oh. So yeah, the whole thing, yes, exactly. So to get to the center of mass, well, let's do them in order, but yeah. So C, so you go 2 meters in the positive x direction, and 0 in the y direction and 0 in the z direction. It works the same way to get to D. You just go 2.5 in the positive x instead of 2. And then the center of mass at E, yeah, in the positive x direction, you go, the whole thing is 2.5 meters. We're going to the midpoint, so 1.25. For y, it doesn't matter because the weight force is vertical. And then for z, it's 0. So this 0 here, it's not really at 0y, but that's like we just moved that force along its line of action. Yes, right. Any questions about finding those? And for this one, now that we have all these, let's choose the about point at the origin. That's a good place for it anyways, because that's where we have the most unknown force components. Okay, so now I'll set up the table. Rho, force, moment. I'll do that force R first. So the R vector goes from the about point to where the force is applied. What is it for R? 0, yep. We have to do everything in 3 dimensions now. The force vector is Rx, Ry, Rz. And the moment is 0, 0, 0. We do, yeah, because, so, you know, our 6 equations are going to come from the 3 components of the force equation and the 3 components of the moment equation. Okay, so now let's go to the weight force. Those 2 cable forces are going to really be a pain. Let's save those for the end. So the weight force, the rho vector, well, since we chose, you know, anytime your about point is the origin, your rho vector is just the coordinates where the force is applied. Does that make sense? Because the rho vector is just a vector that goes from your about point to where the force is applied. Okay. So the rho vector is just going to be 1.25, 0, 0. The force is 0, negative 490.5, 0. And that cross product is 0, 0, negative 613.13. Okay, so now we're getting to those two cable forces. So the first one, let's do that force TA. Well, the row vector, I mean, again, because the about point is at the origin, is just going to be the coordinates of A. So that's 0, 1, 1. No, it's not. That's C. Yes, thank you. Okay, 2, 0, 0. And then the force vector, so how are we going to get the force vector? This is where it gets to be a pain. Yeah, so we're going to have to get the unit vector that goes from C to A, and then multiply that by this variable TA. Okay, so the unit vector, so let's do that for, cable A first. So first, let's get a vector that's in the right direction. So our vector U is going to be, so to get a vector that goes from C to A, that's going to be the coordinates of A minus the coordinates of C. So 0, 1, 1 minus 2, 0, 0. So you get this vector negative 2, 1, 1. And now we have to divide that by its magnitude. And so a unit vector in that direction, if you're lucky, your calculator does that for you, is negative 0.816, positive 0.408, positive 0.408. Okay, and so that force then is this unit vector times the variable TA, so negative 0.816 TA, positive 0.408 TA, positive 0.408 TA, yep. Let me see your calculator. Inspire, yes. Just Inspire. Okay, then I'm not sure. We should look at it. But if there's not, it's easy to program it. Yeah, it does save you time. Okay, so now take the cross product of these two. And you get 0 for X, negative 0.816 TA for Y, and positive 0.816 TA for Z. And then the last force is the cable B. Yep.
How does the moment have two directions?
Well, you can think of that as so the direction of a moment is the direction, if you think of a moment as a rotation, the right-hand rule gives you the direction of the moment, okay? So that's just saying that, and the magnitude of that vector, is the magnitude of the moment. So what that says is if you put your thumb in the direction of that vector, okay, your fingers give you the direction of the rotation that it would cause. Okay, I know, we're a lot less used to thinking about moments in 3D like this, but in general, a moment can always be 3D because you can have a vector in any, choose any direction in space, put your thumb in that direction, this moment can cause a rotation in that direction.
And this would have like a pattern on it.
I mean, yeah, I guess you could say that. I mean, it's now that we have forces happening in all three directions, these forces can create rotations in all three directions, you know, about all three axes. Also, if it makes more sense to you, you can think about it as three separate moments, you know, a moment of 0 about the x-axis, a moment of 0.816 TA about the negative y-axis.
Well, I'm saying like, so that's in, it's like 45 degrees in the x.
Yeah, in the YZ plane, yeah.
Well, like if you just like turn and look at it a little differently.
You are right about that, yes.
Get back to the same.
Yes, exactly.
But that just wasn't possible.
Well, you can't do it with all, you know, you can't do it with all your moments because all our moments are going to be in different directions.
That just wasn't like a possible thing that could happen, you know, in 2 dimensions.
Right, exactly. Because in 2 dimensions, you only have one possible rotation. I mean, you have one plane of rotation and you can only go this way or that way, you know. Now you can have a rotation like this or a rotation like this, or, you know, you have all this extra room. Okay, so now TB. The row vector is 2.5, 0, 0. And now we have to do the unit vector thing again for cable B. First, a vector that's in the direction of this cable. So, you know, we want our unit vector to go from B to B. So we're going to do that as the coordinates of B minus the coordinates of B, and then normalize it. So this vector U, before we get it as a unit vector, is 0, 1.5, negative 2. Minus 2.500. And so you get the vector negative 2.5, 1.5, negative 2. And then a unit vector in that direction, you know, figure out the magnitude, divide every component by the magnitude, and you get negative 0.707, positive 0.424, and negative 0.566. So the force vector is that unit vector times TB. So negative 0.707 TB, positive 0.424 TB, and negative 0.566 TB. And now take the cross product of those two vectors, and you get 0 for x, 1.42 TB for y, and 1.06 TB for z. Okay, so our 6 equations, are 3 for forces and 3 for moments, are going to be, you know, we're going to add up all the x components of forces and set it equal to 0. Add up all the y components of forces, set it equal to 0, z components. And then we'll do the same thing with each component of the moment. I said at the start, you know, we only have 5 variables that we're solving for. We normally, you know, we would expect to get 6 equations. What's the equation here that isn't going to be useful? Can you tell from looking at this? Yeah, the x component of the moment equation just says 0 equals 0. So I'm going to cross that out. That's almost always true in problems that are given in textbooks. Like any problems that I looked up in textbooks are that way, because they don't use reduced row echelon form, so they have to set them up in a way that you can do it with substitution. That usually means like reducing the variables somewhat, but okay, so the equations are Newton's second law says Rx, Ry, Rz plus 0, negative 490.50 plus negative 0.816 TA, positive 0.408 TA, positive 0.408 TA, plus negative 0.707 TB, positive 0.424 TB, and negative 0.566 TB is equal to 0 vector. And then the moment equation says, I'm going to write out all three components, but 0, 0, negative 613.13 plus 0, negative 0.816 TA, positive 0.816 TA, plus 0, 1.42 TB, 1.06 TB is equal to the 0 vector. And, this X equation, you can see, doesn't help. And so we have 5 equations for 5 variables. There's equation 1, 2, 3, 4, 5. And if you do this with reduced echelon form, you get that the R vector is 527.5, 210.2, and negative 35.1. Those are all newtons. And the tension in cable A is 429.6 newtons. And the tension in cable B is 247.7 newtons. And so based on those calculations, you could maybe, make sure that you had a thicker cable in that position, cable TA, cable A, and you could use less material in the cable for B. Any questions about that? Okay. Well, that's all. So for the weekend, I guess I'll give you a couple of these 3D problems to work on. And then if you have questions on Tuesday about them, I can answer questions or do problems in class. Okay, that's all.